So, I said in the first talk, all I just wanted to do was to show you a lot of use cases and some core concepts. And the basic message is that the spatial computing has already transformed our society, right? Billions of us use GPS, we use Google Maps, we use Uber, but this is only a beginning. You're going to see a lot more, in the coming decades, because as everybody gets aware of these capabilities, they are going to think of many, many new use cases. Okay. But this would not happen unless we support it, right? Individually, we should think of use cases. Universities, as you know, they need to also think about and have institutions which will promote this thinking, because it's a very, very interdisciplinary thinking, and some of that is starting to happen. If you think about places like Harvard, it created a GIS center. University of Minnesota, we have used spatial. So these are sort of reminiscent of the computer centers of 20, 30 years ago. Okay. See, computer science is a very new discipline. If you were thinking about, when was the first undergraduate degree granted in computer science? Not that long ago. It's only 50 years. Okay. So if you were in 1960s, you heard about first computer being bought in India at JNU campus. But back then there would be a computer center. It was a nice air-conditioned room, and in summertime that was the best place to be. So a lot of us learned programming because of that. But it was a shared facility. Everybody on campus who wanted to use computer came there, right? And there were people who helped them out. That's what is happening with GIS today. And many university campuses have done that, including Minnesota, where you have service staff and so on. They come and teach you short courses. They help everybody use the data sets and so on. And then people are trying to develop the curriculum and so on. So a number of master's degrees in GIS have been floated around in many universities. And now it's coming down to not only undergraduate, but even in high school, we are now creating an advanced placement course. And those curriculums and those efforts are afoot. Okay. And similar support is important from the government side as well in terms of supporting these things. And many governments, particularly large countries, are actually doing that. In fact, we were just recalling, Milak was mentioning, so 2009 I was involved in another major effort to get a center, a GIS center in IIT Bombay Computer Science Department. And Department of DST here had a really nice sponsor which was trying to get GIS program going in many places in the country. So if you connect back to the government, they all realize this is a technology needed, particularly in large countries. And they are very supportive of creating these and so on. So that's sort of the overall message of the first part, that it has a lot of societal application. And it also generates a lot of new research problems. Otherwise, a computer scientist like me will not be in this space, when rest of his colleague 20 years ago were not even really interested in that. So this is end of the the lecture, and I'll pause here if there are any questions and so on. Otherwise, we'll take maybe a 5-minute short quiet time and then go to some tutorial exercises. Yeah. So issues, questions, and so on. Okay. And this will tell you the resources. So this cover article actually shows some of this. They would often have a week or 2 weeks of discussion on those. But let's maybe think about the second question, when to use which one. Okay. So in terms of when to use which one out of these hundreds of coordinate systems, I would say there are two broad kind of things to think about. Okay. So one thing is if you are in a very sophisticated computerized environment, which is what typically most of us will be, right? So if you have rich set of software and so on, then your main consideration is to worry about the data sets. Okay? Because data sets will come in different projection systems. But if you have a software like ESRI's ARC Info or Postgres, it will understand all of them. Okay? And you will be able to convert and mix and match. Okay? So if you have a reasonable software, then your concern primarily is to understand your data sets. Okay? That's the key thing. Okay? So now we can think about some of the major data sets, and I will also invite audience participation. Okay? So as I mentioned, if you are looking at GPS, US GPS, it picks a particular coordinate system, and you should at least know the name, WGS84. If you are looking at Google Maps, again, consumers, a lot of us look at that, it will use another one called Web Mercator. It's not exactly Mercator, but it's called Web Mercator. Okay? But at least you know that these two in a native format are different reference system. Okay? So if you are trying to mix the two, then you certainly need a software which understands both and can match them. Okay? So that's the key. Now you can go beyond and say what are the other major data set or that you might use and what reference system they may use. Okay. So do you have a particular data set that you are thinking about?
OpenStreetMaps. So maybe particularly something like you want to do an evacuation route kind of an application, and you want to send people from one location to some other location. How do we go about it? Because OpenStreetMaps gives you the lat long.
Right.
How do we go about the elevation or how is the projection to be more accurate towards our results?
Okay, so let's come to disaster response and emergency management. That's your central question. Okay, that's a very good question. So disaster response, at least in US, community has been coming together to define a single unified reference system. Britain and US have been working on that as well. So disaster response, has many data sets. So you really need to deal with coordinate systems. So one of which is road maps that you mentioned. You could use OpenStreetMap and its coordinate system. Okay. The second data set that often comes are various reports, because you may have different people who are affected. They might call from cell phone or other units saying, I'm over here, I need help, right? And those have to be registered. And if they are coming through smartphone, they are probably giving you GPS coordinates. Okay, so those have to be brought together. But you may have to bring to bear other things, like you brought up the elevation map. And the question is, what's the source of your elevation map? So in India, I guess you work with elevation map. Yes. What's the source?
In India, we are working on Lambert conformal conical projections for all the domestic maps mapped by the Survey of India. And your elevation is DTED2. Just Google DTED2. DTED2. That is what is being used. What regarding your question?
But DTED, does it tell you the reference map projection or?
No, sir. These are already processed by Survey of India. They don't need to disclose the source, but you get the detailed map based on that. Now, in India, basic primary disaster relief is worked on LCC and Indian Everest coordinate system data. This is India Everest 84. We are migrating to WGS 84, but it is a long-run process.
And they probably should not migrate. So India Everest one, this is another story to know about. Okay, WGS, India Everest, and so on. These are all, in some sense, ellipsoidal coordinate system. Okay. See, the first approximation of the Earth is a sphere, and at sphere level, you can define a unique sphere, latitude, longitude. All right, but Earth, as you know, is not a perfect sphere. Poles are a little bit squashed, right? And equator is a little bit broader. I will show you a short video also shows that visually. So it's really ellipsoid is a better approximation. But unfortunately, there is no unique ellipsoid. There are hundreds of ellipsoid, and each country has picked its own ellipsoid. So the one you heard, the Everest one, is probably the favorite ellipsoid for India.
For India, Bangladesh, Pakistan, and up to Himalayas.
Up to Himalayas.
Okay. Everest.
Everest, okay. But if you go around other countries in the world, China would have its own ellipsoid. Okay. In fact, US has dozens of ellipsoid. Each state in US has its own ellipsoid. Okay. And that's where the value of this software comes. So you have to know where the data came from. Okay. The US GPS, its main goal was global navigation by Department of Defense. So it picks something which is not very accurate, at any place, but globally it's a reasonable thing. So within India, probably your average ellipsoid is more accurate than the GPS, right?
So in fact, the US DOT has given in the GPS a configuration which is called India-Bangladesh mean grid system.
Okay.
So the moment you come into that configuration, you automatically get into the Everest and the LCC.
Okay.
So then your airline is about 10 meters from the point of.
Okay, wonderful. And so in your software, it automatically switches
Yes,
to that.
in the GPS which are being look like Garmin, Magellan, which are coming into India.
Okay.
They have a configuration for India-Bangladesh mean grid system.
Okay. Okay. So then they are coming with richer software
Yes.
to do that.
Definitely.
Okay. Good. So hopefully that helps. But as I said, if you are in a rich software environment, then your primary concern is the data source. Okay. And because your software will understand all of them. But if you're getting data source 3 or 4 or 5 different ones, each one has different map projection system, and you overlay them on top of each other without thinking, you will be really off. So if this video is on, I will show you a small example which is a teaser. Let's maybe do that. It's an excuse for self-promotion also. But let's watch this. It has one of these examples, so it finds that example.
So can I add one more point?
Yeah, please go ahead.
What happens is when you open up Google Earth is a satellite image. So there are a lot of problems related to reflectance. Open up Srinagar, Dal Lake is green. It is not shown as a lake because of the undergrowth in Dal Lake. So you first have to segregate the data from a normal geographic map vis-a-vis what you are getting on Google Earth. And then you work your disaster plans. Because there is number of water bodies which play when it comes to disaster. So reflectance pattern has to be studied of that area before you make your disaster plan. And second thing you have to study is tectonic plates.
Okay.
In case of an earthquake, what is going to crumble first?
From there. All right. So if you are not in a rich software environment, if you are on paper map and so on, then your problem is completely different. Okay, then you will need to know your purpose and then ask which paper map am I going to use. Okay. If the Wi-Fi comes on, I will show you a little video to see how much error could happen if you.
By using a lat long kind of a scenario, we will go wrong. That's why we wanted to think of a projection which will
OSM is
be more
LCC
accurate.
based.
Sorry?
OSM is LCC based.
I didn't understand that.
Survey of India OSM is LCC based projections. If you take it on LCC, Lambert Kanokono, it will give you correct distances.
So even your distance function, if you were in OGIS simple feature type, when you compute distance, you can specify the projection system. Okay? You can say I want to use spherical distance on lat long, it will give you one distance. Or you can say I want this average projection, it will give you a different distance. Okay? So depending on the projection system, the result of distance and area and all will change. So what we are saying is if you use the ellipsoid specific to India, your distance calculations would be much better. And you are saying about within 10 meters? That's very impressive. Okay. But certainly if you do lat long, it will be better than flat map. But it probably won't be as accurate.
But the problem with the lat and long is basically we all do simulation on the flat map only. So then the problem comes when you need to transform lat long to the 2D dimension.
Okay.
And then there is a point of come like we need to go through the georeferencing. If we don't use the georeferencing, is there any other way to convert the lat long to 2D?
So tell me about your 2D use case and 2D map. Are you?
For the transportation system, suppose we need to generate a map of a particular city or the area.
Right.
So then we need to even in OpenStreetMap, the SMO simulator is there, simulation of urban mobility. We used to where simulate the mobility of the urban area.
Okay.
There basically they use only the 2D maps. So then the problem arises how to convert that land. Ultimately, if we use this kind of art surface,
Okay.
mass of the earth, so it's very cumbersome to every time to multiply with the latitude and longitude. So is there any other way to convert that to the...
Do that. Okay, so let me maybe come back to that. See if the video plays, we'll at least for everyone have one simple example. Okay. Should we try the video?
And simple coordinates describe a sphere. It's easy to compute spatial relations in this imaginary world. But the reality of our Earth disagrees. The globe bulges at the middle. The land plane has mountains and valleys and roads wiggle and wave. This world of the real, a new sort of computing is needed. Join us as Shashi Shekhar discusses how computers have come to understand the peculiar dimensionality of our real world, spatial computing. Minneapolis sits alone, over 500 kilometers from the nearest major city. But make your way here and you'll find the University of Minnesota's spatial computing research, led by Shashi Shekhar, confronts quandaries posed by our often messy physical world.
So latitude and longitude is a coordinate system centered at the center of the Earth. It's a spherical coordinate system. But we all know that Earth is not a perfect sphere. So US GPS measures a ellipsoid and uses one. Europeans measure with their own satellites and they have different. So for example, if you think about a major landmark, the English ellipsoid and the GPS can be 100 meters off at that point.
But where the physical world provides challenges, it also offers opportunities that spatial computing can exploit. For example, the technique of autocorrelation.
In other words, nearby things are not independent of each other. So if you try to imagine, what would physical world look like if each point had an elevation which was independent of all other points, including its neighbors. Spikes, yeah, it's the Bryce Canyon in Utah.
Features of the physical world dictate which algorithms are fastest and best. These results are sometimes at odds with classical assumptions.
So for example, in the roadmap storage, roadmap database, back then everyone was using geometric techniques. But when we started ranking those methods to store roadmaps, turns out the ranking measure was based on graph theoretical properties, the number of edges cut. And we saw, oh, that's a huge blind spot in our literature.
As literature has progressed, with advances in spatial computing affecting all physical spaces, not just geographic ones.
One could also say that your medicine should be delivered to only specific locations in your body, right? So you can imagine that in the future, these medicines will be delivered by some carrier molecular devices, which will be able to know their location in human body in terms of organs.
But even if restricted to geographic applications, advances in spatial computing could make a big difference.
So we live on the surface of the earth, and lots of our lives is affected by that. And that's what spatial computing is about.
Find out more in the contributed article, Spatial Computing, in the January 2016 issue of Communications of the ACM.
Actually, there is one other projection video. Let me show that. This was very simple, but you kind of saw it. Greenwich, there is a big difference. Let me go to this site, and there is a very nice. This is a 5-minute video on projection system. Very well done. Just watch that. This map projection.
eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maths uses cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the map used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator projection. If you're American, you've probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa, by a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we'll end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
The Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World. Really?
So if you want to see a map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up, but on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Wickel triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of the projections. And just remember, there's no right answer.
uh,